Now, in today's lecture, we begin with the topic of mean temperature difference in a heat exchanger. We are going to first define the term, what we mean by the mean temperature difference in a heat exchanger, and then we are going to derive expressions for the mean temperature difference for various flow classifications, that is for parallel flow, counter flow, the three cases of cross flow and so on. Let us consider some heat transfer surface. Let me draw heat transfer surface like this, across which heat is flowing. Some heat transfer surface. A hot fluid, let us say, is flowing on the top side. Let us say this is the hot fluid. And let us say the cold fluid flowing on this side. Flowing on the other side. This is the heat transfer surface. This is the heat transfer surface, and let us take some elementary area dA on this heat transfer surface. Let us say somewhere on this heat transfer surface we take an elementary area dA. Anywhere on this heat transfer surface. Let us assume that the temperature of the hot fluid at dA is Th on this side of dA, and the temperature of the cold fluid on the other side of dA is Tc. Now, we know from our knowledge of heat transfer that the heat transfer rate dQ across this elementary area dA, the heat transfer rate dQ is given by U, the overall heat transfer coefficient, may consider fouling, multiplied by Th minus Tc, which we are calling as delta T, multiplied by dA. This is our expression for the heat transfer rate. And if I ask you what is the total heat transfer rate across this heat exchanger, you will say, well, all I need to do is to integrate this expression over the whole area A of the heat transfer surface. So, the total heat transfer rate in the heat exchanger, the total heat transfer rate, let me add the word rate here, in the heat exchanger Q will be given by the integral U delta T dA, where the integration is carried out over the whole area A of the heat exchanger. So, the integration is carried out over the whole area of the heat exchanger. That is the total heat transfer rate. Now, if I assume that the overall heat transfer coefficient is a constant, not varying over the surface of the heat exchanger, if U is assumed to be a constant, if U is assumed to be a constant, some constant value, then we can say the expression for Q simplifies to the Q is equal to U can be taken outside the integral delta T integrated over the area A. Now, I define the quantity mean temperature difference as follows. I say define mean temperature difference. By the expression delta T m delta Tm stands for the mean temperature difference in the heat exchanger, and I define it as delta Tm is equal to 1 upon A, the integral of delta T dA, the integral being over the whole area A of the heat exchanger. Thus, if I introduce this definition into my expression for Q, I get thus Q is equal to U A delta T m. That is the expression that I get. And what we have here is the basic performance equation of a direct transfer type heat exchanger. So, let me just sort of circle it to give it its due importance. I will put a circle, put a rectangle round it to say this is an important equation which we are going to use for calculating the performance of a direct transfer type heat exchanger. This is our basic performance equation. Put a rectangle to give it its due importance and say this is the basic performance equation this is the basic performance equation for a direct transfer type heat exchanger. So, suppose I have a direct transfer type heat exchanger, whatever it be, shell and tube, plate fin, plate, whatever it is. If I want to calculate the Q, the amount of heat transferred per unit time in that heat exchanger, I will need to know the value of U, the overall heat transfer coefficient. I will need to know of course, the heat transfer area in that heat exchanger, and I will need to know the mean temperature difference for the heat exchanger. I will need to have some expression for calculating the mean temperature difference. The mean temperature difference will depend upon the temperatures of the fluids, two fluids, the hot fluid and the cold fluid at the inlet and the outlet. So, I need to find ways of calculating delta T m based on my knowledge of THI, THE, TCI, TCE. That is what I am going to do next. Now, our next job is find expressions or ways of calculating delta T m for parallel flow, for counter flow, for cross flow, all the three cases of cross flow. That is going to be our next job. We have defined a delta T m. How do we get its value for different flow situations? So, let us look first at parallel flow. Let us say now our next job is to derive an expression, mean temperature difference in parallel flow, derive an expression for the mean temperature difference in parallel flow. That is our next job. Now, let us first look at a parallel flow heat exchanger, a typical parallel flow heat exchanger. Let us say, let me for the moment not to confuse you, let us put a cover on the lower side, so that we focus attention on the upper part of the figure. Here we have a parallel flow heat exchanger. The flow rate, this is the shaded, the hatched lines indicate the heat transfer surface, the area is A, and this heat exchanger has a length L in the direction x, x is measured from this side, the left hand side, it has a length L, a breadth B at right angles to the paper. So, the area A of this parallel flow heat exchanger is A is equal to B L. The flow rate on the hot side is m dot h, as you can see it is shown here. The flow rate on the cold side is m dot c, shown here. The hot fluid enters with the temperature THI and leaves with the temperature THE. The cold fluid enters with the temperature TCI and leaves with a higher temperature TCE. we would like to derive an expression for the delta Tm, the mean temperature difference for this parallel flow heat exchanger. That is our job. Now, let us now, before we start deriving the expression, let us just for a moment qualitatively see the picture before us. These are the temperature profiles on the hot side and the cold side. On the hot side, the fluid is entering with the temperature Thi, and as it goes along the length of the heat exchanger, it is giving up heat and reducing in temperature to a value The. On the cold side, the fluid is entering with the temperature Tci, and as it goes along the length of the heat exchanger, it is increasing in temperature to a value Tce at the exit. So, let me put arrows to show the directions of the temperature profiles, the flow directions. So, the temperature difference between the hot and the cold fluid at the inlet is Thi minus Tci, and that is delta Ti. We will call that as delta Ti. Similarly, the temperature difference at the outlet of the heat exchanger would be Thi minus Tce, and we will call that as delta Te. So, that is the position. Now, the delta Tm, the mean temperature difference for this heat exchanger, is going to lie between these two extremes. One extreme is delta Ti and the other extreme is delta Te. Delta Tm is going to lie between these two extremes, some value in between this. We want an expression for delta Tm in terms of Thi, Tci, The and Tce. Consider, let us now derive the expression. So, let us consider some elementary area dA of this heat exchanger. Consider an elementary area dA, elementary area dA, which will be equal to B, the breadth of the heat exchanger, which is a constant, into dx. Right. Let us consider some elementary area and the heat transfer across it. Before we do that, let us make two assumptions which are reasonable assumptions. Let me put those down and then continue with the derivation. We are going to make two assumptions. Let me show those. First, we will make the assumption that the overall heat transfer coefficient U is a constant. The value of U for this heat exchanger all over the area of the heat exchanger is a constant. So, U is a constant, that is assumption 1. The second assumption we are going to make is the heat exchanger is adequately insulated, so that there are no heat losses to the surroundings. What we mean by this is the hot fluid, whatever heat it gives up, whatever loss of enthalpy it has, all that energy flows to the cold fluid. None of that energy is lost to the surroundings. And usually this is a good assumption, because that is the purpose of a heat exchanger, to transfer heat from a hot fluid to a cold fluid, not to lose the energy to the surroundings. So, heat exchangers are adequately insulated, so that the heat losses to the surroundings are in fact negligible. So, let us make the two assumptions: U is a constant and heat losses are negligible to the surroundings. Therefore, enthalpy change of the hot fluid will be equal to enthalpy change of the cold fluid. Now, let us continue with our derivation. I said to you, let us take an elementary area dA of the heat exchanger, which is equal to B dx. What is the heat transfer rate across this area dA? We know that already from earlier. dQ is nothing but U delta T dA. dA is nothing but B dx. That is the so many watts is the heat transfer rate across the elementary area dA. Now, when this heat transfer takes place, because this heat transfer takes place from the hot side to the cold side, the enthalpy of the hot side fluid decreases by this amount, and the enthalpy of the cold fluid increases by this amount. The enthalpy decrease of the hot fluid is seen by the decrease in temperature. So, over the length dx, the temperature of the hot fluid decreases by dTh. So, we will say this must be equal to the change in enthalpy on the hot side m dot h Cph dTh, and that must be equal to the increase in enthalpy on the cold side, which is equal to m dot C Cpc dTc. Notice I have put a negative sign on the dt on this first one. Why? Because dTh will be negative in the positive direction, which I am measuring from the inlet. X is being measured from the inlet. So, dTh, the temperature of the hot side will go on decreasing in the positive direction. dTh will be a negative number. So, I need to put a negative sign in order to get an enthalpy change and equate this to the heat transfer rate across the area dA. So, these are all equal expressions. This is the heat transfer rate across the area dA, this is the enthalpy change on the hot side, this is the enthalpy change on the cold side, and they have to be all equal. Now, delta T is nothing but Th minus Tc. Delta T is Th minus Tc. Therefore, d delta T, if I take a differential, is nothing but dTh minus dTc. I can write this as, now I have an expression for dTh out here and an expression for dTc out here. So, instead of dTh, I can write minus dq upon m dot h Cph, and instead of dTc, I will get minus dq upon m dot c Cpc using these two expressions. And further, for dq I can write the expression, the first expression. So, I can say this is equal to minus u delta T b dx. I am substituting for dq from this expression here, the first one, and into bracket 1 upon m dot h Cph plus 1 upon m dot c Cpc. That is what I will get. So, d delta T is equal to minus u delta T b dx into 1 upon m dot h Cph plus 1 upon m dot c Cpc. Let us integrate this expression from inlet to outlet. So, let us say, let us rewrite this expression as d delta T upon delta T, bring the delta T to the left hand side and integrate this expression from inlet to outlet, that is integrate inlet, at the inlet the value of delta T is delta T I, at the outlet it is delta T E. So, expression integrated from inlet to outlet, this must be equal to minus 1 upon m dot h Cph plus 1 upon m dot c Cpc is a constant, it comes outside the integral, u is a constant, so it comes outside the integral, b is a constant, comes outside the integral, only the dx remains inside. So, integral of dx 0 to L, the whole length of the heat exchanger. If I do this and integration now, by the way, before I go further, let me say where, be careful here, delta T I is T H I minus T C I. I mentioned that earlier, but I am writing it down now. Delta T E is equal to T H E minus T C E. Delta T I is the temperature difference between the hot and the cold side at the inlet end. Delta T E is the temperature difference between the hot and the cold side at the exit. Now, therefore, we get with the integration I will get log to the base e delta T e by delta T I, that is the left hand side, is equal to minus 1 upon m dot h C P h plus 1 upon m dot c C P c multiplied by u multiplied by B L, which is nothing but A, the area A of the heat transfer surface. And that is equal to, I can write that further as equal to minus. Now, for m dot h C P h, I can write T h I minus T h e and divided by q, which I will take outside. So, I will take 1 upon q plus for m 1 upon m dot c C P c, I can write T c e minus T c I and again a q which I take outside. That is the total heat transfer rate in the heat exchanger is nothing but m dot h C P h T h I minus T h e and multiplied, the whole thing multiplied by u A. So, I can further simplify and finally get my expression which I am looking for. I get q is equal to, now the expression in the final form is q is equal to u A delta T I minus delta T e divided by the logarithm to the base e delta T I by delta T e. That is the final expression that I get. This is the performance equation for a parallel flow heat exchanger. This is the performance equation for a parallel flow heat exchanger. And if you compare this, compare with our basic performance equation for a direct transfer type heat exchanger, what was that? Comparing with the general equation q is equal to u A delta T m. If I compare this, this is our general equation for any direct transfer type heat exchanger, then you can see for parallel flow, comparing with this, we say for parallel flow delta T m is equal to delta T I minus delta T e divided by logarithm to the base e delta T I by delta T e, and delta T I is T h I minus T c I, delta T e is T h e minus T c e. So, we have achieved our objective now. For parallel flow heat exchanger, if I know the temperatures of the two fluids at the inlet and outlet, I know delta T I know delta T e, I can calculate delta T m for parallel flow. Once I go to my basic equation, q is equal to u A delta T m, and I will get the heat transfer rate in the heat exchanger. This is what we have achieved. Now, we are going to do the same thing for counter flow. One by one, as I said, first we will do for parallel flow, then for counter flow. So, our next job is to proceed for counter flow in a very similar manner. So, I will not spend that much time in this derivation. Our next job is derive an expression for the mean temperature difference in counter flow. Derive an expression for the mean temperature difference. We will proceed more or less in the same fashion with some small differences which I will point out as we go along. First, let us look at a counter flow heat exchanger, a sketch of it as we did for parallel flow, and then put down the equations again. But we will move a little faster because, as I said, the derivation is somewhat similar. Let us look again at the top half of this figure rather than the whole figure. Here is our counterflow heat exchanger. Length L, breadth B at right angles to the paper, flow rate on the hot side m dot h, flow rate on the cold side m dot c, same as earlier. Now, but notice however, fluid entering on the hot side enters with a temperature T h I, leaves with a temperature T h e. Okay. The fluid on the cold side enters from the other side at a temperature T c I and leaves with a temperature T c e. So, now the directions of flow are reversed, keep that in mind. We will again consider an elementary area dA which is equal to B dx. So, we have got the same sketch excepting that the two fluids are flowing in opposed directions. So, T h I and T c I are on the two sides of the heat exchanger. Let us look at the sketch of the temperature profiles now. Here are the two temperature profiles. On the hot side, this is the fluid entering at T h I, decreasing in temperature as it goes along the length of the heat exchanger and leaving at a temperature T h e. On the cold side, it is entering on the other side, that is where T h e is entering on this side, and as it goes along the length of the heat exchanger, the cold side fluid picks up heat and leaves at a temperature T c e. So, the two temperature profiles now look something like this, and we will define delta T I as T h I minus T c e. Keep that in mind, which is different from the earlier definition of delta T I. Delta T I will be in counterflow will be T h I minus T c e, and delta T e in counterflow will be T h e minus T c I. So, keep that in mind as we go along. Now, let us proceed with the derivation. As I said, the derivation will be more or less on the same lines, there will be hardly any difference, we can move a whole lot faster. We will make the same assumptions, make same assumptions. What were they? Number 1, u is a constant, and number 2, no heat losses to the surroundings. Change of enthalpy on the hot side is equal to change of enthalpy on the cold side. The decrease in enthalpy on the hot side is equal to the increase in enthalpy on the cold side. Consider again an elementary area dA. Consider an elementary area dA equal to B dx. dq, the heat transfer rate, proceeding more or less in the same fashion as earlier, dq, the heat transfer rate across dA will be u Th minus Tc, temperature difference from the hot side to the cold side, multiplied by P dx, that is equal to minus m dot h Cph dTh. Notice the negative sign is because dTh will be negative in the positive x direction, and that is equal to minus m dot c Cpc into dTc. So, the difference now is I have a negative sign out here also, because in the positive x direction the temperature on the cold side is also decreasing. Let me show that sketch again just to illustrate what I mean. This is the x direction, the positive x direction. In this direction Th is decreasing, Tc is also decreasing. So, dTh and dTc are negative quantities, therefore, I need to put a negative sign on them to get a positive value of dq. So, that is the difference between parallel flow and counter flow, this negative sign. Now, we proceed with the same algebra. We can write d delta t is equal to dTh minus dTc, which is equal to minus dq upon m dot h Cph plus dq upon m dot c CPC, and using again the first and second and the third equations which we had earlier, if we do a little algebra, we will get this is equal to further this is equal to minus u delta t minus u delta t b dx in bracket 1 upon m dot h CPH minus 1 upon m dot c CPC, and then I integrate from inlet to outlet. So, I will get d delta t upon delta t is equal to minus 1 upon m dot h CPH minus 1 upon m dot c CPC u b the integral over dx, and performing the integration I will get the logarithm to the base e delta t I by delta t e is equal to minus 1 upon m dot h CPH plus minus 1 upon m dot c CPC multiplied by u b l, which is nothing but u a, where keep in mind however that in counter flow delta t e is T h e minus T c I. Note this difference from parallel flow, and delta T I is equal to T h I minus T c e. These definitions are different from parallel flow, that you should note. Therefore, we can write further this log to the base e delta T e by delta T I is equal to minus 1 upon q into bracket T h I minus T h e minus T c e minus T c I. These are the changes in enthalpy on the hot side and cold side, the whole thing multiplied by u a, or finally our basic performance equation q is equal to u a delta T I minus delta T e divided by logarithm to the base e delta T I by delta T e. Notice we have got the same equation as we got for parallel flow. It is the same equation, there is no, in terms of symbols we have the same equation, but delta T I and delta T e mean different things in parallel flow and in counter flow. They are defined differently. That has to be always kept in mind. In fact, let me just draw a sketch here, so that again there is no confusion. These are the temperature profiles on the hot side and on the cold side. This is T h I decreasing to T h e, and this is on the cold side T c I increasing to T c e. This difference T h e minus T h I T c I is equal to delta T e. This is delta T e, and this difference out here is delta T I. That is what has to be kept in mind. T h I minus T c e is delta T I. Now, if I again compare with our basic performance equation, comparing with our general performance equation, Q is equal to U A delta T m for any direct transfer type heat exchanger, I will get delta T m in counter flow is equal to delta T I minus delta T e divided by the logarithm to the base e delta T I by delta T e, where delta T I and delta T e are as defined just a moment ago. So, this is my expression for the mean temperature difference in counter flow. So, now if I have a counter flow heat exchanger, I know the inlet temperature on the hot side and cold side, the outlet temperature on the hot side and cold side. I know how to calculate delta T m for that counter flow heat exchanger. The moment I have got the delta T m, I can say the heat transfer rate for that counter flow heat exchanger is U, the overall heat transfer coefficient, into the area A into the delta T m in counter flow as calculated from this expression. Now, we go to the next case. No, before we go to the next case of cross flow, let me look at one special case of counter flow which is worth talking about. So, for a moment, let us talk about one special case of counter flow before we move on to the cross flow situation. A special case of counter flow. What is that? The special case of counter flow which we want to look at occurs when m dot h Cph is equal to m dot c Cpc. Suppose we have this situation. The product of the flow rate and the heat and the specific heat on the hot side equals the value on the cold side. Then it follows since Q, the change of enthalpy on the hot side and the change of enthalpy on the cold side are numerically equal, it follows that Thi minus The must be equal to Tce minus Tci. The changes of temperature on the two fluids must be equal, or I can rewrite that as Thi minus Tce is equal to The minus Tci. Thi minus Tc is nothing but delta Ti in counter flow, and The minus Tci is nothing but delta Te. So, we have delta Ti equal to delta Te for this special case. Now, if I substitute into my expression for the mean temperature difference that delta Ti is equal to delta Te, substituting into the expression for delta Tm, we get, if you do it you can see straight away without even my substituting it on paper, we get an indeterminate quantity. You will get 0 upon 0. We get an indeterminate quantity, 0 upon 0. So, what do we do if you have a situation like this? Calculus, our knowledge of calculus tells us that if you want to calculate the value, we need to differentiate the numerator and denominator and apply what is called as L'Hopital's rule. So, let us define delta Ti divided by delta Te. Let us say this is equal to some quantity P, in which case our expression for delta Tm becomes delta Te P minus 1 divided by the logarithm to the base e of P, and we want to find this in the limit as P tends to 1, as delta Ti tends to delta Te. L'Hopital's rule says, apply L'Hopital's rule, this is from our knowledge of calculus. L'Hopital's rule says, differentiate the numerator and denominator with respect to P. So, you will get delta Tm is equal to the limit P tends to 1. I am differentiating now the numerator, the denominator with respect to P, delta T remains the same. P minus 1 when differentiated with respect to P gives me 1. The logarithm of P when differentiated with respect to P gives me 1 upon P, and if I now put the limit P equal to 1, I will get this is equal to delta Te. So, the application of L'Hopital's rule gives me the value of this indeterminate quantity delta Tm, and what we find is that delta Tm is equal to delta Te, which is nothing but delta Ti. And in fact, in this particular case, what really happens is the following. What we really get is the temperature profiles on the two sides are two parallel lines like this. This is on the hot side, this is on the cold side, this is delta T I, that is T H I minus T C E, this is delta T E, which is T H E minus T C I. And if you have two parallel lines, it follows for the temperature profiles, if you have two parallel lines, it follows that delta T M must be equal to delta T E, must be equal to delta T I. That is really what we are getting. So, for the special case, the temperature profiles tend to be straight lines, two parallel lines, and delta T M becomes equal to delta T I or delta T E. So, this is one special case of counterflow worth talking about. Now, let us move on to cross flow. We want to now get expressions or get values for the mean temperature difference in cross flow. First, we have three cases there, mind you, you recall. We have both fluids unmixed, that means we have fins on both sides which prevent the fluid from moving in a transfer direction and mixing with itself. Then we have one fluid mixed, the other unmixed, or we have both fluids mixed. So, let us take first case 1 in cross flow, both fluids unmixed. Now, this is how the temperature profile is going to look in this case. This is the hot side fluid and this is the cold side fluid. This is the hot side fluid, this is the cold side fluid. The temperature on the hot side fluid is T H I, uniform everywhere while entering, this is T H I. The cold side, while entering, it is uniform, but now since it is a fluid in which no mixing takes place, it is both fluids unmixed, any fluid particle at T C I which enters here is going into come into contact with hot fluid at T H I and is going to heat up the most. On the other hand, a fluid particle entering at this side at T C I will come into contact with hot side fluid on the other side, which is at a lower temperature. It has been cooled in moving through the heat exchanger. So, this fluid particle is going to heat up less. So, while leaving the heat exchanger, the cold side profile is going to be something like this. In the same way, you can see the hot side fluid is going to be something like this. So, the temperature of the cold and the hot fluids will now be functions of x and y. Keep that in mind. Now, let us write down the expressions that we get and see how far we can go. So, let me first make a statement. Both, for this case, cross flow, both fluids unmixed, both TH and TC, both TH and TC are functions of x and y. X and y are what we had earlier. Let me just go back to the sketch. X is this direction in which the cold fluid is moving, y is the direction in which the hot fluid is moving. We need two directions now, it is a two dimensional problem, unlike parallel flow and counter flow, which were one dimensional problems. So, we had only the x direction there. All right, that is important that you keep that in mind. Now, we have variations in x and in the y direction. So, TH and TC are functions of x and y. Consider again an elementary area dA, consider an elementary area dA which will be equal to dx dy. It is a two dimensional problem. So, we can say dq, the heat transfer rate about cross dA is equal to u Th minus Tc into dx dy. If we assume u to be a constant and integrate over the whole area A of the heat exchanger, we will get q is equal to u integral, we will now have to do a double integral Th minus Tc dx dy, where the integration over x is from 0 to L and the integration over y is from 0 to b. Let me go back to the sketch that we had and show again This is the area A of the heat transfer surface, hot fluid flowing on one side, cold on the other side. In the x direction, the length is L, in the y direction, the length is B, flow length is B. So, B L is the heat transfer area, x has to be integrated from 0 to L, y has to be integrated from 0 to B. That is what we are doing in order to find out the total heat transfer rate. Therefore, we can see straight away, comparing with our basic equation, comparing with Q is equal to U A delta T m, that is our basic equation. We have delta T m in cross flow is equal to, this is for cross flow, delta T m for cross flow is equal to 1 upon B L, the double integral in 0 to B, 0 to L, T h minus T c multiplied by dx dy. That is our expression for delta T m in cross flow. So, you can see it is more complicated than we had earlier. We have now got a double integral which has to be handled. So, the determination of delta T m is going to be much more complicated. It has been done numerically. So, we do not have to worry about it, we will get the results, but it is not as straightforward as it is for parallel flow or for counter flow, which were one dimensional problems. Now, let us look at the other case, case 2. What is case 2? One fluid mixed, the other fluid unmixed. Let us assume the cold side fluid is mixed and the hot side fluid is unmixed. Now, what we are going to get is something like this. This is our cold side fluid. Let me draw its temperature profile. This is our cold side fluid. Uniform while entering, which is TCI, and this is where the fluid is entering, cold fluid entering. This is my direction x, this is my direction y. Let us say the hot side fluid, let me draw again a sketch there, the hot side fluid. This is the temperature profile at the inlet, uniform while entering. So, this is THI that I am showing, fluid temperature profile while entering on the hot side. This is THI. Now, the hot side fluid is unmixed, therefore, its temperature profile will be non-uniform at the exit, something let us say like this. The fluid on this side, which is unmixed, will get cooled more, the fluid on this side will get cooled less, and we will have some non-uniform temperature profile with TH being a function of x and y. TH will be some function of x and y. On the other hand, on the cold side, since we have got mixing, any fluid particle that enters here and gets heated, any cold particle that enters here and gets heated, the moment that happens, they can also mix transversely with each other and get to a uniform temperature, then proceed further and again receive heat from the hot side. So, on the cold side, we are going to have a uniform temperature profile because of the mixing taking place on the cold side. We are going to have a uniform temperature profile like this on the cold side. This is the temperature profile on the cold side, like this. This is TCE, this was THE here, which is a function of x and y. TH which was function of x and y, and THE which was varying. So, we should note that whereas TH is a function of x and y, TC because of mixing is a function of only of x. So, this is going to be the situation when we have one fluid mixed and the other unmixed. And the third case which we have is when both fluids are mixed, in which case we are going to get something like this. Let us draw that situation. We are going to have mixing on both sides. So, we will have the fluid on that side uniform temperature while entering and uniform temperature while leaving, mixing on both sides. So, I am going to have now a temperature profile because of the mixing on both sides, which is something like this. So, this is TCI, this is TCI, this is TCE, also uniform because mixing is taking place on the cold side. Similarly, THI like this, on the hot side and THE on the cold side. So, this will be THI, the temperature profile on the hot side, this is THI, and this will be THE, uniform while leaving because of mixing. This will be THE. So, in this case now TC will be a function of x and TH will be a function of y. So, it is still a two dimensional problem, but the TH is a function of y only and a TC is a function of x. So, if we have got a more complicated situation, these integrations which for finding out the mean temperature difference for these three cases, the integrations to find out delta Tm have been done numerically. The integrations for the three cases of cross flow have been done numerically, and the results are presented in the form of a correction factor F The results are presented in the form of a correction factor F. F is defined as F is equal to the delta Tm in cross flow divided by the delta Tm if the arrangement had been counterflow. That is how the results are presented in the form of correction factor F, which is delta Tm cross flow upon the delta Tm if the arrangement had been counterflow. If the bulk exit temperatures on the hot side and the cold side if the bulk exit temperatures, they may be non-uniform, but if I get a mean value and call it the bulk exit temperature, if the bulk exit temperatures on the hot side and cold side are THE and TCE, then delta Tm, if the arrangement had been counterflow, we know that delta Tm in counterflow will be THI minus TCE minus THE minus TCI, the logarithm to the base e, THI minus TCE divided by THE minus TCI, delta Ti upon delta Te. So, the final results based on this numerical integration are given in the form of a correction factor f. F is equal to the delta Tm in cross flow upon the delta Tm if the arrangement had been counterflow. We know how to calculate the delta Tm in counterflow. Now, next time I am going to tell you how f has been determined and how it is presented graphically, so that once we get a value of f, we can get the delta Tm in cross flow.